My name's Justin Hart, and I'm faculty with the Department of Computer Science at the University of Texas at Austin. I'm also part of the Learning Agents Research Group, which is directed by Peter Stone. I'm also the Assistant Director of Texas Robotics, which is a research consortium at UT Austin, bringing together a cross-disciplinary group of researchers from across the entire campus. And the major motivator for my research, the major thing that I've been thinking about over the past few years is what do we need to do in order to make it practical to see a robot in every home and workplace? And I'm going to start with a story that I think is familiar to all of you. I probably could get away with my premise without setting it up even. We're all sort of familiar with the story that robots started in factories, right? In the 1970s, we had these companies building robot arms, and they basically just run G code, like the code that runs a 3D printer or a milling machine or a lathe. And they do tasks like welding together the frames of automobiles or maybe spray painting them. They're able to do this because these are repetitive motions and they don't require a lot of computation or sensing or artificial intelligence on behalf of the robot. And of course, because these robots have very little sensing and no real AI, so to speak, they're kept away from people. They're put into an area of the factory called a work cell. If a person goes into a work cell, that's a pretty dangerous situation. When you hear about industrial accidents involving robots where a robot has hurt a person, it's generally because the person, not to blame the victim here, but because the person has walked into an area of the factory that they shouldn't. And of course, that was the model, for like 30 years. And in the past 20 years, we've really seen an explosion in robotics. And the first thing that really entered into everyone's sort of sphere was the Amazon Kiva robots, right? This is why we have really inexpensive overnight shipping with Amazon Prime, because the robots are able to very efficiently take over the role of the picker in the warehouse, bringing the goods to the person known as the packer, who then packs them into boxes to be shipped, reducing the labor overhead while making the whole thing more efficient. And then more recently, we've seen a proliferation of robot companies. And these are what I would call single purpose robots. These are robots which really only do one job, but often sort of lifting some of the restrictions about being around people. These robots generally do operate in close proximity to people. They have sensing, they have artificial intelligence systems aboard them. They're much more flexible and much more capable than their predecessors. And just looking over the applications in this slide, we've got Fox Robotics, which is a company which has an autonomous forklift, which can unload cargo from the back of a semi-truck, palletized cargo, and then put it onto the floor of a warehouse where it'll be, unwrapped and depalletized and put onto shelves. And then on the upper right, we've got a drone from a company called Pensa Systems. And what this drone does is it takes stock on the shelves of grocery stores and reports that stock back, not actually to the grocery store, but to the companies that sell those products, because that information, as in how prominently displayed is your product and how much of it is on the shelf, is very valuable to those distributors who will then go and approach the grocery stores about displaying and purchasing their product. And then another startup near and dear to my heart, because it's Andrea Tomaz's company, Diligent Robotics, a company which is trying to take away some of the stress from nurses working in hospitals. Nurses spend quite a lot of their time actually going and moving things around the hospital, fetching things from medical cabinets. And by giving this role to the robot Moxie, the nurses are able to spend more time on patient care. And then finally, in the lower right is the Savioke Relay. This is a robot which drives around hotels and provides room service. And if we kind of, look at the theme that I'm looking at here, on the left, the earlier robots are operating in environments with fewer people and less complexity for the robot to deal with. They're operating in environments which can be customized to the robot and in places where they don't have to interpret what people are up to. But then on the right, you have much more interactive systems which are operating in places which are designed for people, not for robots. But despite all that, I think that everyone here recognizes that we're still quite a long way from general purpose service robots in the home. And that challenge led me and my collaborators to form a team to compete in RoboCup at Home. And now I have an intro to what RoboCup at Home is on this slide. I know that many of you have at least a passing familiarity with it, but probably most of you don't have an up-close familiarity with how RoboCup at Home works. So most people, when they think of RoboCup, they think of robot soccer. This is the UT Austin Villa Robot Soccer Standard Platform League team competing with Aldebaran Now Robots, or I guess SoftBank Now Robots, against the Bielefeld team Be Human, which is a nice little play on words, in the finals, I want to say in 2016. I want to say this is the year before I joined UT Austin. And, robot soccer is scored very much like you would expect. The robots basically try to score goals, and the winner is determined by the number of goals that they score. And every year, the federation, the leagues, all try to get what the robots are doing to be slightly closer to human soccer, because the goal of RoboCup is to have a team of humanoid robots play against the World Cup championship team and win by 2050. All right. On the same site, co-located at the same meeting, is RoboCup at Home, which focuses on domestic tasks set in a simulated living space. So not in a simulator like Gazebo, but in a space like this. It's built out of the sort of stall furniture that you would say at conventions and fairs, except that that stall furniture is populated with, furniture. It's populated with couches and televisions. They build a little kitchenette in there and a dining room. And then the robot is supposed to perform tasks in that space. And because I'm speaking to a savvy audience, I know that many of the people competing in RoboCup at Home see this picture and they look at the problem of perception and motion planning and manipulation. But clearly all of you would see that the real complexity in this problem is the fact that these robots are operating in a human environment and they're required to interact fluently with people, which is why all of you should make teams. So just a quick plug, I'm on the executive committee of RoboCup at Home. I help steer the league. If you have input in terms of what you would like to see in RoboCup at Home, what you would like to see at this competition, please drop me an email. I would be happy to have that conversation with you. But another conversation I'd be even more happy to have is to see more people in this room at RoboCup next summer. They're already in the process of taking people. AI HRI is a little late in the year to apply to go to RoboCup at Home. But still, if you are interested in this competition, please do reach out and I'll be happy to help you in your quest to start a RoboCup at Home team. Taking a quick look over the tasks in RoboCup at Home, it does sound a little futuristic for robotics in the current state of the art. And of course, this is a simulated apartment. The tasks are dramatically simplified from what they sound like. But just as a sampling, they're broken into two categories: housekeeper, which focuses on manipulation and planning, and party host, which focuses on human-robot interaction. And the RoboCup Federation really does view RoboCup at Home as being a competition of human-robot interaction. So housekeeper tasks are things like storing groceries, which people really like because they like doing manipulation because it's fun. And that's taking groceries off of a kitchen table and placing them near thematically similar groceries in a cupboard. General purpose service robot is speaking commands to the robot, and then the robot is supposed to perform those commands. And they are more complex than you would expect, but they're still generated from a limited grammar of commands. So you couldn't ask the robot to say, go to Walmart and purchase me a video game. That's not allowed. And then party hosts are the more interactive tasks. So those are things like carry my luggage, which involves gesturing to the robot what bag you would like for the robot to pick up, and then having the robot follow you out to your car. Or for instance, serving drinks, which involves going to a bar and retrieving a drink for the guest. And then these are all divided up into stage 1 tasks, which are kind of the easy mode tasks. Everyone who qualifies for competition participates in these. And stage 2, the hard mode tasks, where the top half of the performers of stage 1 are allowed to complete. And so, let's look at just one of these tasks to kind of see how this works. This is take out the garbage. This is our implementation, and this is us trying it out in our laboratory at UT Austin. When you look at this task, the basic implementation here is a visual servoing task where the robot has a camera in its hand, and it's going to perform an object recognition of the lid of the garbage can. You can see that the robot has to try that funny grasp there to get the handle of the lid. That's because the detector is YOLO, and YOLO won't tell you the orientation of the image, so you can't tell the orientation of the handle going in. And then the robot will plunge its hand into the can to go and grab the bag, and then drive over to what we've sort of designated as the collection area. In the competition itself, it's just outside the door of the arena, but for the sake of all of our sanity while we're testing this repeatedly, we didn't want it to take that long of a trip. So we just have a little box over in the corner, which is where it goes. You'll have to forgive the camera work. That's one of my students with a GoPro, just kind of shooting this to demonstrate testing while we're in the laboratory. And there you go, the robot has dropped off the garbage. There are two basic approaches to solving these problems, which teams take on. The first is to write a different program for every round of RoboCup at Home. And I would say that greater than half of the teams in RoboCup at Home do something like this. They build a library of common capabilities, but each task has a separate program that it runs and is very much different from the others. In 2017, which was our first year competing, actually our first year competing with the new team, we had a team way back when this was founded, and then there was a gap in continuity. That was our basic approach. And then ever since 2018, we've been running a custom architecture, which we built. The idea behind this being that we really want to build a comprehensive general purpose service robot, which is able to do all of RoboCup at Home, to where we could eventually say, hey, robot, go take out the garbage, and that would be what it would do. We're not there yet, but we do implement all of our rounds following this basic framework, and we've ported this framework to our other robots in the laboratory. And this architecture is called the layered architecture for autonomous interactive robots. It looks a lot like classic robotics three-tiered architectures with something sort of deliberative up at the top. In this case, it's hierarchical finite state machines. Basically because we can state what the robot needs to do in each step of the round in the state machine, and then hierarchical because we can decompose some of those tasks. So the task of taking the garbage out of one can involves taking off the lid and taking out the garbage, and then that's repeated by the top level state machine. We also have a planner and a plan executor. Our planner may be a little unfamiliar. Most people are familiar with PDDL. We use a language called Klingo. So when I'm referring to how Klingo does planning, just bear in mind that a predicate in Klingo can be used as the equivalent of an action in PDDL. So in this case, we'll form a task level plan of what the robot's going to perform in the environment. The state machine can invoke the planner because the state machine might have instructions like listen to an utterance that someone speaks to the robot, parse it, and then provide that parse to the planner, right? And then we have a plan executor. And for each predicate that is corresponding to a behavior that the robot should perform or an action that the robot should perform, there is something we call a skill. And so that might be follow someone from room to room, right? Or navigate to a landmark, like go to the garbage can or pick up the garbage bag, right? And so we're able to spit out a plan or process a plan. And then as we step through that plan at each time step, perform the skill associated with each time step. All this goes back down to our knowledge representation system, which is stored in a database. And then different interfaces provide data into that database. So for instance, the computer vision system extracts information about the environment and then stores that as semantic information in our database. And then we have a very efficient mechanism of querying information out of the database and then placing it into the planner. So we're not filling the planner with tons of predicates and tons of atoms, just those that are essential to solve the plan. And so there are many questions you might be asking about at this point. But the one that I'm going to address is how do we ground items in this knowledge base? So the symbol grounding problem or the language grounding problem is another problem that many of you will be familiar with. This is something where you take an atom from your planner, an atom being basically like the apple or the thing, right? And then that's a symbol, but of course that doesn't mean anything physical in the real world. In order to refer to a physical apple, I have to tie that atom down to the robot's percepts, right? I had to go and use object recognition or classification of some variety in order to identify the physical apple in the environment, which is tied to the atom in the planner. The first approach that you might see is ground things as the robot sees them. This is popular in RoboCup at home, partly because there's a time limit on these trials. So if you're passively gathering information through the robot's vision system as the robot drives around, you're being very efficient about the way that you're finding out information about the environment. Basically, the robot can scan its environment while performing other tasks. Now, that's not to say that's the only thing that happens in RoboCup at home. You're given 2 setup days and you can take pictures of everything. You can drop landmarks on the map that describe where everything is. But part of this is made up in the sensing step. Another thing that you can do is you could do something that's sort of plan free. You could accept a command from a human operator, like go get me the apple. And then instead of querying back to your database and forming a plan and then having to ground that, that atom, maybe what you're doing is you begin a scan to search for that item. Like you go into your into whatever representation your program uses, which is still similar to an atom, still something that you need to ground. And then you begin trying to ground it by having the robot look around the room for that item. Our approach is sort of a hybrid of the two. Ground things as the robot sees them, annotating their locations. But if you haven't found the item, for those types of systems, that generally poses a problem. So what we do is we generate hypothetical items for the robot to ground against. So for instance, what I'll do is I'll say, you know, I'm looking for an apple, and then the robot will go, okay, well, the apple might be on in the kitchen cabinet, it might be in the refrigerator, it might be on the kitchen table or on the counter, right? It generates a bunch of hypothetical apples, and then when and if the apple is found, it grounds the real item, replacing the hypothetical one, which is what you can see in this video, which was published in ICAPS regarding our planning system.
Hello, how can I help you?
Are you all able to hear this?
Yes.
Great.
You want me to bring you food from the kitchen, is that correct? Yes. All right, I'll get on that. Which kind of food? Okay.
So here we see the robot kind of scanning the shelves for the hypothetical apple, and it doesn't find, you know, the hypothetical apple on the shelf. So it's going to go and scan other surfaces.
Is the operator here? Yes. Hi. Please be ready to consistent hypotheses. From the request, I assumed a hypothetical annual application that turned out to be false.
So, the robot very politely calls one of the PhD students from my laboratory, Yu-Chen Zhang, a liar, right? But of course, what about that awkward handover, right? People don't hand objects to each other by saying, I will hand you the object in 3, 2, 1, right? That should be smoother, especially in a league that seeks to be a competition about human-robot interaction. And, in all honesty, there are teams that probably could accomplish that and teams that couldn't. So they do try to make it something where everyone can compete. Right now, there's nothing in the rule books regarding having a smooth handover. There has been in the past. But what we've been doing and what I've been pushing, especially for as an executive of the competition, is adding tasks which directly test human-robot interaction and push innovation in that direction. And so to that end, I added a task to the rules called Hand Me That. This isn't my team performing that task. This is the best performer from RoboCup 2019 on that task, TU Eindhoven, a Dutch school. And basically what this task is about interpreting point gestures. And one of the teams demonstrated that their robot was so proficient in interpreting point gestures that the audience in the stands could point at things in the arena and the robot could still interpret what they were pointing at successfully. So here's, their video. There's one of our judges, Alex Moriarty, pointing at an apple, and then the robot indicates that it knows what the object is by touching the top of it. And so now he's going to point across the kitchen at, I think it's a root beer from Australia. First the kiwi and then the ginger beer. And then the robot, successfully indicates that it's found the ginger beer, even in the presence of all those people in the background. So some teams have been doing some really innovative and exciting stuff on the front of human-robot interaction at RoboCup at Home. But, as great as RoboCup at Home is, there are some serious gaps in what it tests and, where it's going. This is definitely intended to be something where we outline a challenge and then everyone goes and competes on that challenge. And then as the league gets good at that, we make that challenge more challenging. We have about a 2-year cadence, one of introducing challenges and letting people do sort of their first performance and then doing a refined, better performance the next year. The demos are impressive, but they are things that are really impossible to solve using current technology. The teams are all given 2 setup days where they thoroughly map the arena. They drop landmarks where the robot should drive to during different instructions in these tasks or different points in their plans. They fully retrain their object recognition systems localized to the country that RoboCup is held in. And there's only going to be a limited set of items in the arena. So they're always basically taking their object recognition network and then retraining the last layer of that network to recognize the 15 to 20 items in the arena. It's still very challenging given the current state of the art, right? That's remarkably difficult. And these are nearly impossible systems to build that are really at the edge of the state of the art. And yet they have nothing like the flexibility that they would need in order to be deployed in the real world doing these tasks, right? And then judges in the arena are really only allowed to give a limited set of commands. So the participants know what they can anticipate that the judges will say or do. And there's a little bit of a bonus point if your robot is able to accept a rephrase of the command. And we have big efforts at UT Austin right now, which are addressing these specific gaps. So over the past few years, we've formed a new research consortium called Texas Robotics. This is an interdisciplinary group with a little over 16 core faculty, 40-something affiliated with the group. We're housed in a new robotics facility that I got to sort of oversee the construction of, which is exciting. We've got a seminar series. We don't have a degree program, but we have what's called a graduate portfolio program, where if you take the classes that we emphasize, you'll get a mark on your transcript that says that you completed the portfolio. And then the thing that has been really exciting for me is that it's increased the bandwidth between different faculty and different departments. So I and a close group of collaborators share a laboratory space, which is reconfigurable. And now we do almost all of our projects together. And this is kind of what it looks like. Here's the view of our courtyard. We have this lovely statue, which is installed by the UT Public Arts Commission. Here's a group from my class working on their semester projects. I have a project-based class for undergraduates in robotics. A group of students working on our Boston Dynamics spot. And then you can see our new RoboCup at Home Arena housed in the Anna Hist Gymnasium facility. Called the Anna Hist Gymnasium because it's a historic place, so we can't, tear it down or rename it. But it is actually a very beautiful building, especially post-renovation. One of the things that has grown out of Texas Robotics is a program called Living and Working with Robots. This is something that started as a collaboration during the pandemic. We built a robot delivery system where you could hail a robot for contactless delivery using a cell phone application, and it'll bring you a lemonade from our lab. And it's an interdisciplinary group run by the UT Austin Bridging Barriers program, which is the thing that funds interdisciplinary groups internally. And then as a sub-program of that, Good Systems. These are systems which try to maximize social good, which try to be, ethical and just generally positive for the world. And what we've been doing is developing robots with real jobs on the UT Austin campus, robots which we don't intend to take down and dismantle at the end of our experiment, but leave in those jobs at least for the duration of a very long study, like 2 or 3 years, but possibly forever. We are studying the entire ecosystem. So right now we have a team of design ethnographers who are working with the UT library system to see how the jobs of librarians work and what they might possibly use robots for. And they'll still be in there after we deploy the robots, seeing how they're actually being used. Then we have the people over at Texas Robotics over at our facility designing and deploying the robot systems for that real job. And then human robot interaction research on the deployed system will happen once it's deployed, of course. So we're trying to ask some big questions here. What jobs should these robots be doing? Does what we do in the laboratory match the real world? So if we do something like a semantic mapping task, will it work in a real library? Will it work on the real routes that the robots need to take to do these jobs? And possibly the biggest is, how can we prepare robotics for an industry when robotics is as big as the internet, right? If you look at the profile of a robotics company right now, the people working in them are mostly PhDs who, really, studied for years, specifically in robotics to do that job. Can we arrive at standard components? Can we have a standard stack similar to the LAMP stack on the web, right? Currently, we're working with the UT Austin library system as our sort of first client for all this, or our first site for all this integration. The other thing we have that sort of deals with the real world is the NSF NRT. That's a National Research Traineeship Program. It's a program under which you hire PhD students, but it's also intended to be transformative to the way that you educate people at your institution. And this is the Convergent, Responsible, and Ethical AI for Roboticists program, or Create Roboticists. And this will have another graduate portfolio program incorporating a strong ethics component. Students will participate in research projects accentuating ethical AI and robotics, and then they mandatorily will have internships and workshops grounding what they're doing in the real world. This was funded for $3.5 million by the National Science Foundation. So, all that said, I'm going to change gears and dive deeply into a problem that I've been looking at actually with several participants in this workshop or this symposium for a few years now. And that's what happens when there are delivery robots everywhere, possibly going between the libraries of UT Austin, on crowded sidewalks and in hallways. And this has become a popular problem over the past few years. This is social navigation. We focus a lot on the specific sub-problem of looking at social cues as they relate to social navigation. So, for those of you who haven't been reading the literature on this problem, picture an autonomous vehicle. It's, on the highway. Its job is to stay in its lane, follow traffic laws, use turn signals, follow its route, not hit other cars. And even though, this is all pretty well defined, we still don't do it well enough to make this commercially viable yet, right? And then think about how people navigate past each other. There's no laws telling you how to, walk past other people, at least not in the US, and they seem different everywhere, right? We pass at very close distances. People often brush into each other. If they're not, they're passing each other a couple inches. And often we're walking straight towards each other. We communicate with position, speed, gesturing, tension, and body language, right? So can we build robots that do this well? Think about, this video right here from YouTube. These are students in an acting program, and, they're walking down the hallway, they're not paying attention to each other, and then, inevitably they kind of block each other's paths. And the title is Awkward Situations, the Hallway Dance. This wouldn't be awkward if people were bad at this. People do this very fluently. So as a subset of the social navigation problem, the one that we've really looked at the most is the hallway passing problem, which is to say humans pass each other gracefully, but robots struggle to understand the intentions of the people and struggle to make their own intentions understood. We really came at this problem initially as part of the Building-Wide Intelligence Project. This is a real-world deployment of service robots that we've built over in the computer science department at UT Austin. This is a conjunction with Peter Stone, though Rafe Mirsky in this workshop also works with this project. So it's a real-world deployment. We've got a fleet of these robots. We decided to build them in-house and cheaply so we could have many of them. So there's 6 of them. And iterations of this project have responded to verbal commands to do things like perform object delivery, provide directions to pedestrians in the building, deliver messages. And they're really intended to operate constantly during the workday. So if you come over to the NHIS Gymnasium, to our robotics facility, you should be able to see one of these robots operating when you're there. But if you look at current navigation algorithms, basically they work like this. The robot goes down the middle of the hallway and then just stops when the person comes too close. And a few years ago, we actually had a problem with that. We had 2 BWI bots operating during our PhD student visit day. And there was a crowd of PhD students looking through the glass into a laboratory. And one BWI bot stopped at one end of the hallway, and the other BWI bot stopped at the other end of the hallway. And they were like bookends, boxing in the PhD students or the prospective PhD students, right? The robots didn't know what to do to get out of the person's way, and the people were very much stuck because the robots took up most of the hallway. Another approach to this is going down the middle of the hallway and treating the person like an obstacle, which works pretty well if you're in an open environment like a gymnasium, but in a constrained environment, that's really not the right thing to do. It's unpredictable and possibly uncomfortable for the people. It can lead to confusion. It can cause all sorts of problems, right? As a first approach to solving this, we wrote a paper where basically we just had a robot use turn signals to communicate its intention to people. We built a simulated hallway as a place to test this rather than blocking up our real hallways. We built it out of cubicle furniture. We built a model of that hallway as 3 traffic lanes, and then we split that up into 3 distances: the distance at which the robot would use its turn signal, the distance at which the robot would switch lanes. So the robot and the person both start on the middle lane, they're heading straight towards each other. And the robot or the person can both choose to go to the the top lane, the left lane, or the right lane, the bottom lane. And then each of these things happens at a different distance. And if you come too close to each other, we call that a conflict, and the robot simply stops. All right, we did a pilot study. We don't need to go into the details of the pilot study, but simply put, the people didn't understand the turn signal. About half of them said that the signal was regarded as the direction that they should walk in, and about half said that the signal said what the robot intended to do. So basically, the results were that chance, that their behavior was not correlated to the turn signal at all. So we came up with a new approach, which is what we call a passive demonstration. What we observed is that once a person saw the turn signal once, they always understood it after that. So basically, if the robot made a turn using the turn signal, the person would understand it. So we just had the robot do this demonstration by making a turn at the start of the hallway before it was close to the person. And then as it came closer to the person, it used the turn signal again in order to get the person out of its way. We set up this 2x2 experiment where there was either the LED and the turn signal, or there was a demonstration and there was no demonstration. And the purpose of doing it as a 2x2 was to eliminate the possibility that the robot's trajectory was informing the person what to do. So this is what it looks like with no demonstration and no LED. So the robot starts up down the hallway and the person starts up down the hallway. And then the person walks into the robot stops, the person walks around the robot, they move on with their lives. The second one is with no demonstration, but with an LED. So the robot starts up down the hallway. You can now see the robot signaling to the person, or you will in a second. There you go. Person isn't sure what it means. And then eventually, you know, at a very close distance, kind of scoots out of the robot's way. Here's a demonstration with no LED. So the robot makes a turn right at the start, rights itself, goes down the middle of the hallway, and then the person is going in the wrong way and just kind of scoots around the robot, right? The robot's trying to make a left turn, but the person gets directly in its way. And there's one thing I forgot to mention. The robot always goes to the left. And that's because we're trying to test people's interpretation of the turn signal. The person, their inclination is always to go to the right. So as long as you know that the person's inclination is always to go to the right, if we're going to the left, we can assume that about 100% of the time, the person and the robot would collide without signaling. All right, so here's a demonstration with the LED. So the robot makes the LED turn and then signals again, and the person clearly understands it and gets out of the robot's way several meters in front of the robot. And we saw that this reduced conflicts quite a lot. So, you know, no demonstration, no LED resulted in conflicts 100% of the time. Whereas with the demonstration in the LED, it was only down to 20% of the time. But of course, people don't have turn signals, and we were looking for something that people would understand the very first time that they saw it, because we don't want to have to train them to use the robot. So we asked, what role does gaze play when people pass each other in a hallway? We performed a human study where we had experimenters vary their gaze patterns. So a person would look with either congruent gaze, they would look in the direction that they intended to go. Incongruent gaze, they would look opposite the direction they intend to go. Or no gaze, they would look down on their cell phone. And what we found is that using incongruent gaze had a statistically significant effect on how often people came into conflict with each other. And we measured that based on how many times they physically bumped into each other, which makes this my favorite IRB that I've ever been a part of. So basically, we just went to a busy hallway and we had experimenters look in various ways, and we measured how many times they ran into other people. This is basically what it looked like. Here's Raith doing congruent gaze, incongruent gaze, and looking down at her cell phone. So now the question becomes, does gaze work better than turn signals? So we want to contrast a robot making a turn signal against a robot making a gaze cue. We implemented a virtual agent head on the robot so the robot could kind of look around. And then we just did that as a test against the LED. We can skip looking at what the LEDs look like and skip right to our experimental video. And here we go. So the robot is now going down the hallway. Unlike last time, the LEDs are mounted only on the front of the robot, so you can't see when they go off. My apologies for that. But you can see that the robot comes into conflict with the pedestrian who eventually walks out of the way. And then condition 2, the robot's using the gaze, and you'll be able to see that the pedestrian gets out of the way of the robot really early. The gaze cue is really intuitive to the pedestrian long before the robot starts executing its turn. So in the LED condition, we ended up with conflict 100% of the time. Again, remembering that the person is always, or the robot is always going to the left where we expect it to collide with the person. And about 50% of the time, the gaze cue works. And people say, oh, well, what would happen if you just flip the LED, right? Well, nothing, right? We know that nothing would happen because it's not the LED's interpretation which is driving this. The robot's always going the same way. It's just that the person's instinct is always to go to the right. So the next thing that we asked is, what about making the robot respond to the person? What if the robot could respond to the person's social cues and then get out of the person's way? We have begun to study this in virtual reality. So why are we using virtual reality? We can get highly accurate tracking using modern VR systems. We've got a system called the HTC Vive Pro Eye. And what's great is this system has a Tobii eye tracker built into it. So there's integrated gaze tracking, and then we can actually use full body tracking with modules that we can attach to the participant, which is a lot like Vicon. But this instrumentation is only about 3,500 per participant if we're doing full body tracking, only 1,100 per participant if we're using regular tracking. And of course, you can compare that to the prices for the Vicon and the Tobii Pro, which I probably shouldn't do, but there are those numbers, right? So, we built this virtual room and we decided to read gaze as a social navigation cue that the robot would be able to respond to. And of course, there's no robot in the study. All we're doing is measuring how anticipatory gaze is of the trajectory the person will follow. So the task here is to navigate towards one of the targets in the room. A similar experiment was done before by Vaibhav and Helkar, Claudia Perez Jarpino, and Julie Shaw. And they used head pose in a Vicon system. Here we're using eye gaze and virtual reality. We compare against head pose, the walking velocity as a predictor of where the person is about to walk, and then their gaze angle. The actual experiment looks something like this, as the person's walking around the room. And then in virtual reality, it looks something like this. And then the first thing that we notice is that head and gaze yaw will both successfully predict the target of walking very early in the trajectory. However, gaze will do so earlier than the head pose will. So gaze is a really good predictor, at least we think, for deconflicting the trajectories of people while walking down the hallway. And of course, we've done one experiment. We have others in the planning phases. And I'm not going to give away all of our experimental plans, but one of them is to work with 2 virtual reality headsets and full body tracking to investigate the role of gaze and body language in people passing each other in hallways. Another thing that we're doing is we're building this connect hallway so we can study this without instrumenting the participants. Once we've got all the kinks worked out of it, we're going to instrument a real hallway in one of our buildings with this and gather sort of an ecologically valid data set of people navigating past each other. And we're also building social navigation stacks on our robots to enable the robots currently to use the cues that we're able to extract already. But as we get better with this and as we develop machine learning techniques to identify these social cues, to react to those other cues. So just as a way of recapping, what we've talked about, we're working to get robots everywhere. And by everywhere, I mean into homes, offices, and other workplaces. And the biggest obstacle, at least from my perspective, is the presence of people and that these places are designed for people, that we're not instrumenting them for robots. RoboCup at Home is a great avenue for this kind of research, and it can drive real innovation. And of course, one of the big things that's come out of that from us is the layer architecture. We have the living and working with robots and create roboticist programs to try to engage people more in the real world, to take this out of the laboratory and see where the limitations are in these deployments in our labs. And we've done a real deep dive on social navigation, and I've barely scratched the surface in this talk. This is just the stuff that has been published and just the stuff that I'm a co-author on. But at UT Austin, we've actually taken on quite a broad swath of social navigation research, and we have quite a lot of stuff in the pipeline. But we're leveraging robotics, virtual reality, uninstrumented motion capture. And I think that one of the things that makes us unique, that there are other groups who are doing stuff that is similar, don't get me wrong, is that we've got a major focus on body language and social cues. And a lot of the work out there focuses more on the trajectory, though that is very important. So, thank you all for listening, and thank you all for inviting me to give this talk. And if by chance, you saw something that inspired you and maybe you'd like to collaborate, or maybe you're an undergraduate who's here at the symposium and you think you might be a good PhD student, or you're a PhD student who's about to graduate and you think you might be a good postdoctoral fellow with my group or with one of the groups at UT Austin doing this stuff, drop me an email at hart@cs.utexas.edu, or go to my website, my sorely out of date website that needs to be updated, at justinhart.net. So with that, thanks so much.